Welcome back. We're going to continue our discussion on electrophilic aromatic substitution. We've looked at halogenation and nitration in the prior video. This time we're going to do sulfonation. Okay, and as with the other two reactions, we're going to generate an electrophile, but this is the only time where the electrophile that initially attacks the ring is actually neutral. So when you have this combination, this is sulfur trioxide plus sulfuric acid. So when you have this combination, okay, first let me write the product because some of you may not be interested in what I had to say about the mechanism. So whenever this combination is there, you're going to add an SO3H to the ring. Okay, this is what you're going to add to the ring. Okay, even though that's not what you generate initially, if you think about it, just like we said, we added a Br, we added an NO2 to the ring, you can really add the SO3H anywhere on the ring. Okay, this is what you're going to add. I'm just giving that as a shortcut before I explain the mechanism. Okay, now I keep repeating, we are always, when this is the combination, this is what will get added to the ring. Now, because this ring is just by itself, it doesn't matter where we add. But if we have a substituent already on the ring, then we still add this, but whatever the substituent that's on the ring will guide where this will go on the ring. Right now, it has an option to go anywhere on the ring, right? So whenever you have this combination of reagents, this is what gets added to the ring, okay? But right now, it's just a clean, uncluttered ring, so it can go anywhere on the ring to all 6 corners, but only once, okay? You cannot add 6 of this, just once. But say you have something already on the ring, say a substituent's already on the ring, then where this SO3H goes on the ring is guided by what's on the substituent, okay? That's a brand new topic. It's very, very easy, trust me. That's very easy, okay? So is this. But this is how the mechanism works for this. I'm going to show the mechanism for this because this is very unique compared to the other two reactions where the electrophile follows the same exact resonance mechanism that I show for the first two. So only for this one, I'm going to explain the mechanism because it's just exciting to understand the science behind the chemistry here. So here's your benzene ring, and basically your SO3 looks like this. This is the structure of SO3, okay? So the double bond uses, the benzene uses its double bond to connect the carbon to the sulfur, and in the process, one of the double bond comes back to the oxygen. Now, as I said, whenever a double bond is lost, it's a positive charge. Whenever a double bond comes back to an element, it usually is negative. So here's what's happening. Again, I don't expect you to memorize any of this because I don't really think you can just memorize science and say you understood something, okay? Again, I'm going to attach the sulfur here. Now, we didn't disturb 2 other double bonds. Only one of it got disturbed. So the bond came back, so it's a negative. And the positive charge goes here, okay? Whichever side you attach the element, the other side gets the positive charge. If you go back and look at the other 2 structures, now keep in mind, you also have a hydrogen to start with, right? Because carbon has 4 bonds. Now this is 2, so the other 2 must have been hydrogen. And I've also shown these in the other 2 reactions, okay? Now, H2SO4 in water also exists as HSO4 minus, okay? Again, like I said, all of this is, some of it is Gen Chem stuff, okay? So this comes and grabs this hydrogen here, okay? And this bond comes back, okay? So that leaves you, technically at this point, we're done almost with the product. Okay. Now, there's more sulfuric acid in the medium. Okay. It's just not like because I wrote one, there's only one drop of sulfuric acid. There's more sulfuric acid, and the hydrogen gets donated. If I can actually write the sulfuric acid as HHSO4. If I write it this way, the hydrogen gets donated to the negative charge, leaves you with the product. Okay. This is what I meant by, if you see, that's SO3H. So that's what, this is the product. Okay. That's why I said all you're doing when you have this combination is essentially adding SO3H to the ring. Okay. And I keep repeating, right now the ring is uncluttered. So any of the electrophiles that's coming in can go anywhere on the ring. But when we learn the next set of topics, where when we have a substituent on the ring, then we have to guide the incoming electrophile to a certain position. Okay, right now I haven't even mentioned that to you. So when you have this combination, if you don't want to care about the mechanism, at least remember you're adding SO3H to the ring. All right. I'll see you back with alkylation and acylation. I'm just going to do that in one single video so that I can keep the video time fairly short and crisp. So I'll wait for that one.